Hello again, and welcome to another session of Monday Night Calculus. My name is Curtis Brown, and I'm joined by Steve Kokoska and Tom Dick. Super excited to have these guys here this evening with us, answering some of your questions that have been posted on Facebook. Go ahead and give us a shout out from where you're watching. And if you're a student or teacher, we're super excited to have any of our students out there joining us. Please don't hesitate to put questions in the chat box. We'll be watching that, and I'll be making sure that Steve and Tom have opportunity to answer your questions live, along with the ones that have been asked ahead of time. So Steve, without any further ado, because I know we only have about an hour, so I'd love to give you a chance to start talking.
All righty. Thank you very much, Curtis. I'm going to share my screen here, see if all this is working tonight. How's that looking?
Looks great.
Okay, let me make
as does your lighting this evening. Everything looks you've got new light there, so that looks
Thank you very much. All right, well, great to be with both of you again this evening. Curtis, Tom, there are some great questions on the AP Calculus Facebook page this week. Many of these still have to do with limits, which is understandable. That's the beginning of the year. And again, there was some great questions here. I'm going to do a few and try to answer a few, and then I'm going to lead into a little bit of technology, and I'll hand it over to Tom, and then eventually I think it will come back to me. And please feel free to send your questions via chat to Curtis, and I'll remind you once again that Curtis will take questions ahead of time if you want to send an email. That would be fine too. I do monitor the Facebook page, but I think Curtis would be happy to take them also.
I would be happy to. My email will come up here in the chat in just a second. And also, Steve, I want to point out that you've pulled these and given credit to the folks who have asked the questions. I think that's awesome to be able to see their questions out there. So this was from Alexandra.
Yeah, I'm not exactly sure where all of these questions came from, but I'm trying to attribute to the person who posted it on Facebook.
Yeah, sure.
So this one's from Alexandra, and this limit involves this rational function. And at least in my mind, as I look at this, there are at least 3 good limit questions here. And let's take a look at some of those. So the very first one is kind of a basic one. We want to take a look at the limit as x goes to 2 of this rational expression. Now, one of the very first things I teach my students is, well, let's see what happens if we substitute in 2, if we try what I call direct substitution. Now, I'm not going to go through that in great detail with you, but if you plug into the numerator, you get a 0. If you plug in the denominator, you get a 0. I'm not going to get into writing equals 0 over 0 here. We'll talk about that when we get the L'Hopital's rule. But look, in my class, if I get 0 over 0, this is an indication that I need to do something, either algebraic, or I need to make a geometric argument, or okay, a little bit farther on in the year, in the academic year, maybe I have to use L'Hopital. So in this particular problem, early on in the year, one of the techniques we learn is a little bit of algebraic manipulation. So I'm going to factor both the numerator and the denominator. And I'm lucky here. I have some cancellation. The x minus 2's will go. I'm going to pause for a minute. I'm going to take a look at this function and compare it with this one. This is the way that I see this in my weird way of doing things. Those 2 functions are exactly the same, except for their domains. They're exactly the same, except at x equal 2. So if I want to know what this function is doing at x equal 2, I can ask, what is this function doing at x equal 2? And how do I find out what this one is doing at x equal 2? Well, I'm lucky here. I can use direct substitution. And when I do that, I get a minus 5/2. So that's a nice, I think, basic limit problem that we would do at the beginning of the year that's based on this idea of algebraic manipulation. And there's a little bit more going on in the background too there about domains and why you can do that. Okay, let's put that aside. I'm going to present a little graphical evidence of this limit in a minute or two, but let's hold that limit answer aside for a minute. Well, now I want to take a look at the limit as x goes to 4 from the right of this expression. Well, once again, I'm going to write this a little bit differently. I'm going to simplify it. I'm going to cancel out the x minus 2's because I know these two expressions are exactly the same everywhere except at 2. So I'm going to look at the easier one. Now, this next notation I'm going to introduce as my own. I don't think this would be accepted on the AP exam. I think they would just want you to not write anything here, but this is the way that I teach this in my class, and I certainly allow this as students work through this limit. As x approaches 4 from the right-hand side, well, the numerator is pretty easy. That's just going to 4 plus 3, or 7. What's the denominator doing? Well, it's getting closer and closer to 0, but through small positive numbers. And that's the way that I denote that in my class.
Sure.
And now that makes this quotient, I think, easy to interpret. The numerator is getting closer to a constant 7. The denominator is getting smaller and smaller positive. And so that drives the whole expression, the whole quotient, to positive infinity. Now, we can get into a discussion here about whether or not we can write equals infinity. In my opinion, we can, because we as mathematicians understand this notation. It doesn't mean that this limit is equal to some number called infinity. It means it describes the behavior of this limit, that it increases without bound. Now, there was another question. I didn't post this one, Curtis, but there was another question related to this. Was something like, well, what if a student evaluated this and wrote DNE does not exist? Well, I would accept that in my class. This is a little bit more descriptive, but that's also true. And that begs this question. On a multiple choice question on the AP exam, would you ever see a limit like this with two choices, one of them being infinity and one of them being does not exist, DNE? And in my opinion, you'll never see that. The College Board or ETS is not going to make you choose between these two. They will give you one or the other. So I wouldn't worry about that. I think we as mathematicians understand this notation. We know that means that the limit does not exist, but we can describe this behavior specifically.
So Steve, I got a question while you were asking that. Came in from Michael Carson asking about something I think we're going to have to, we'll probably talk about in a couple of weeks or so, but we can address it now. When using the product rule or quotient rule, do you need to simplify after you've applied those two? And one of those two, and I don't know that I can answer that one. So
well, first of all, there's no product rule or quotient rule here. I'm not taking any derivative.
Right. Not related to this particular question, but just in general.
Oh, I see. Okay. Yeah, I guess we'll get to that one. Maybe if you could formulate that a little bit more specifically and send it to you, we'll take a look at that.
Yeah, I think that'd be a good question. Mm-hmm.
Okay.
I think in general, what may be going on there is there's no need to simplify.
Once we've done the work and applied it, we're not simplifying it further.
Yeah, if you've done the calculus work, you don't have to simplify
the algebra.
Though there are going to be instances where simplification may still be useful to you because you need to answer some other question. But if the answer is correct as it stands, I mean, you could even have something like 2 plus 3 doesn't need to be combined to be 5.
Sure. Okay.
So me and Steve,
Michael, let us know if that Michael, let us know if that kind of clarifies things for you, or if you have a further question. I think that would be good.
I'd also add, Tom, I think that one might have to simplify in order to get the correct expression in a multiple choice problem.
Exactly.
Sure.
Yeah.
Mm-hmm.
So not only in free response where you might have to find, a 0 or something like that, but sometimes the multiple choice force you to simplify.
Yeah, that's a really good one. And if there are people out there on the chat who are readers or just teachers out there want to answer some of these questions, I think that's always a good thing to see that happening in the chat as well. I didn't see any responses, but I think that'd be a good thing to keep that chat going.
All right, so let's take a look at the limit as x goes to 4 from the left-hand side. Well, I'm going to do the similar simplification. And I'm going to use similar notation. Once again, the numerator is going to 7. This time the denominator is going to 0, but through small negative numbers. And so the way that I think about this is I have 7 divided by smaller and smaller negative numbers, which drives that whole fraction to negative infinity. So once again, this limit does not exist, but I can describe that behavior as the limit goes to minus infinity.
Hey,
and here's it.
Hey, Steve.
Yeah.
I'm going to interrupt you one more time. We're
Please.
doing this live, right? So I got another question for you directly to the notation that you're using here. And I got it from Marianne Guzman asked, so the plus and the minus in parentheses, you mentioned you didn't think would be acceptable on a free response as notation. So maybe what would be acceptable notation there might be a good thing for us to talk about.
I think, in my opinion, it would just be nothing and minus infinity, plus infinity there. I think you could go off to the side and do some scribbling, some scratch work.
Okay, but just not to include that in your response,
right,
or at least as saying that that's equivalent to something. Okay.
Right. So there are several things, Curtis, as you know, that are acceptable in my class,
right,
not on the AP exam. And so I don't think, you know, as readers, we wouldn't understand that. And it depends on who the chief reader is, of course. If it were me, I'd accept that. But we don't know. We don't know who the chief reader will be at this time if you see a problem like this on a free response. So I would just do the scratch work on the side and then arrive at your answer, minus or plus infinity in this case.
That's fair.
Okay.
Thank you for that.
So here's a graph. I'm sorry, Tom, go ahead.
You know, I was just, your notation here, Steve, actually gave me pause to think a little bit about this exact question. And it occurred to me that if a student actually wrote to the side what they meant by those symbols, that would be, you know, if they said, hey, by plus in parentheses, what I mean is the quantity is approaching 0 through positive numbers.
Yeah.
Then I think a reader would be rejoice and say, okay, I understand what is meant by that person's notation because they explained it to me.
Sure. Okay. I'm going to try once again, Curtis. Here's some graphical evidence. Here's a graph of this function. And as you might expect, there is indeed a vertical asymptote at x equals 4. We can see that to the left of 4, the function is going down here to minus infinity. To the right, it's going up to plus infinity. And here's this first limit we found as x goes to 2. Indeed, the function is actually continuous there. Or at least it looks like it is, isn't it?
It appears to be.
It appears to be. This original function here, this original function does not have 2 in the domain. So in fact, it might be hard to see, but there should be an open circle right there. Because that 2, x equal 2, is not in the domain of the original function, but we can see that the limit is a minus 5/2. So that's a cool problem. It's a lot of neat things going on in there. There are probably some other limits we could look at, but that's a nice basic one here as you learn about some algebraic techniques and also learn about vertical asymptotes. Very cool.
So Steve, would it be okay for me to show a little technology right
Sure.
here?
You want to try a little technology on this one?
Okay.
Absolutely. Hang on. We'll try to stop. There we go. How's that?
Okay. Give it a shot here. And Curtis and Steve, you can let me know, are you seeing my TI-84 screen?
Yes,
Yes,
sir.
sir.
Okay, fantastic. So you can see I've actually entered that same function as my Y1 that Steve was examining those limits on. And I just want to take a look at a graph of it in a standard window here. Standard window on the 84, I think it's minus 10 to 10 in both directions. And that actually turns out to be not really square scaling because the screen's wider than it is tall. But we can see that evidence of that vertical asymptote at 4 with the positive limit coming from the right, negative limit coming from the left toward 4. But at x equal 2, Yeah, it looks like a solid graph here. It'd be great to see that hole show up. And really the trick to do that is just to choose a window so that your discontinuity actually lands on a pixel. So I'm going to do this same graph. I'm going to go over to Zoom and use Zoom Decimal. I end up using Zoom Decimal a lot in calculus because I know my pixels are exactly worth 0.1 in each direction. So it hits right on the integers. So a lot of my examples are going to look pretty nice. And so here's that same graph in a Zoom Decimal window. And look what's happening here at x equal 2. Sure enough, there's a hole there. And
That's really handy.
Yeah, and it's something, you know, as a teacher, I really want students to see that it's not me drawing the hole, the calculator has this gap. And we might say, well, is that just a burned out pixel? Well, let's trace over to x equal 2. Sure enough, there is no y value there. It's undefined, and it's pretty compelling stuff. So of course, it's just the numerical stuff we've got going here. But like say, Zoom Decimal window, especially for these functions where your removable or non-removable discontinuities are happening at integer values or nice fraction values, that Zoom Decimal window, you're much more likely to be able to orchestrate that whole. All right,
yeah, that's a really good.
Tom,
that's a really good calculator skill there.
Tom, I know you're way better at this than me, but my trick for doing this is to always create a window on the x-axis. So then I don't worry about Zoom Decimal, although that's very nice to trace. But I pick my window, so I'll go 2 maybe, and then I'll go 3 to the left and 3 to the right or whatever. My
right, I got you. Yeah,
and then it's forced to sample there. Yeah. Yep.
Yeah. Cool. So in your X-min and your X-max, you're just adding or subtracting the same amount from your target value.
Right.
Yeah.
Right.
Oh, that's almost sounding like a delta.
Very cool.
Sorry, I had to throw that in. All right. Okay, I want to stop my share.
The math jokes will roll all night, I'm sure.
All right. Here we go.
Put your favorite math joke in the chat. We'll watch for those.
All right, I'm going to try this one. This was a cool question from Andy via Verge. And of course, Verge has created these circuits. And this was a really cool problem for a couple of reasons, I think. I think we often see this type of a problem on the multiple choice portion of the exam. And I think what they want us to do, what they want students to do, is to recognize this limit as the definition of a derivative. And so I wrote the definition of a derivative right here. F prime of A is equal to this limit expression. And so what I need to do is to look at that limit, stare at that long enough, and recognize, hey, wait a minute. That's just the derivative of the sine function at pi over 6. And so the derivative of the sine is the cosine. And so I can get this very easily by just taking the cosine of pi over 6, the square root of 3 over 2. Now, I think that's what Verge had in mind, but someone I think brought this up, and I'll just mention this briefly because I think there's something tied into one of the questions on a recent exam here. Let's suppose that somebody looked at this and didn't recognize that as the definition of a derivative and said, well, wait a minute, I'm going to try to attack this by using a trigonometric identity. I'm going to take the sine of an angle plus an angle. So I think what I did is I used the sine of a plus b here, and I expanded that first expression, sine of pi over 6 plus h. Now, before I get to this step, there is a desire, there's this burning desire to take pieces of this expression and take limits, but you can't do that. For example, I'd kind of like to just look at this and say, well, wait a minute. I know that as h goes to 0, the cosine of h is going to 1, so I'll just plug in a 1 there. But you can't just take pieces of an expression and evaluate a limit like that. And the reason that I bring that up is there was actually a problem on one of the forms in the past couple of years, I think it was an online forum, where this sort of thing came up, where a student took limits, like pieces of the expression, and took a limit and arrived at the right answer, but flukily, just lucky. You can't do that. So here's a way that I might attack this, and I'm going to leave a little bit of this to you. What I did is I combined this term and this term, and I factored out the sine of pi over 6. I've got that expression. And I left this term alone. And then I wrote this as a limit of a sum is the sum of the limits so long as they exist. Now this is kind of cool, because you might recognize these two limits and where they show up. And in fact, we talked about at least one of these a couple of weeks ago. So I'll leave that to you and how you would evaluate that. I'll leave it at that. That's a good one. Okay, now I don't think Verge had that in mind, but that is another way to attack this, especially if you have looked at derivatives of trig functions already.
Did anyone out there try this one? I'm curious to find out if anybody tried this one. I'm going to ask them to put it in the chat, because that is a really interesting one. And certainly I'd love to know if they came at it from the direction that you
right down below here. Yeah.
Did. Yeah. Mm-hmm.
All right, let's take a look at number 3 here. This is a great problem.
Hey, Steve, would it be okay if I jumped in again?
Oh, sorry, Tom. Sure, absolutely. Absolutely.
Okay.
Okay, here we go. There you go, sir.
All right. Okay, so I'm hopefully back on my 84. Can you guys see that okay?
I can see it.
All right, great. Just for grins, in this Y4 here,
yes.
I just thought, what you were looking at sine of pi over 6 plus h. I said, well, what if we just made, instead of pi over 6, make that the variable? And I chose actually not that small of an h value, 0.1. So if you look at this, what I've got is it's a difference quotient for sine of x with h equal to 0.1. So I've got sine of x plus 0.1, the minus sine of x, all divided by 0.1. Now, I was just curious, what would the graph of that thing look like? So, well, let's take a look.
Oh, I see you're grouping parentheses. That's good. Okay.
So this is the graph of that difference quotient. And by golly, that graph looks familiar to me.
That sure does.
And I have to be honest with you guys, when I first saw this, I was actually flabbergasted that it was that close to looking like a cosine curve, because that's not that small of an h value. But,
correct. Yeah.
But it's I thought of this just because Steve was using the definition of derivative at a point, and that's how we segue to the derivative as a function, as we imagine doing that same process at each and every value in the domain for which we get a limit. And so this is a way to do that. And in fact, this is what that numerical derivative is based on here, 84, is they use a really small value of h, as well as they do a limit, difference quotient from both the left and the right and average the two. So, cool. All right, back to you, Steve.
All righty, sir. Here we go. All right, so my problem number 3 is from Zach Sarver, and this is a terrific problem. When I was reading this and trying to solve this, it made me think an awful lot about problem solving and how do you teach problem solving? One of the most difficult ideas, concepts to teach, I think. Maybe you become a good problem solver just by solving lots of problems, but this is a great one. Let me show you how I solve this. So we have the graph of this expression y, and it says it crosses its horizontal asymptote at the point 6 minus 5. And this is so typical of an AP calculus question. What's the value of m plus a? So we have these two constants up there in that expression, m and a. What's that sum, m plus a? Well, I thought a little bit about this, and here's the way I started. Look, it says it crosses its horizontal asymptote at that point. So I know right away that the horizontal asymptote is y equal minus 5. So I'm part of the way there. Now, if I know that the horizontal asymptote is -5, and I've got this rational expression, I ought to take a look at the limit as x goes to infinity, or maybe x goes to -infinity. I'll get there. Curtis, don't let me forget that.
Don't let you forget.
Don't let me forget the limit as x goes to -infinity.
Okay.
So I'm going to look at the limit as x goes to infinity of this expression, and a typical way that we solve this, and I know that there are some quick ways to do this, but typical way that we do this is that we divide both the numerator and the denominator by the highest power of x in the denominator, which is x cubed. And if I did all of that correctly, I'm left with this expression, and now I can argue as x goes to infinity, this goes to 0, this goes to 0, this goes to 0, and I'm left with m/1, or m. Now, I've already determined that the horizontal asymptote is y = -5, so that tells me that m is equal to -5. Okay, Curtis, here's your cue.
My cue. Don't forget to go to -infinity and beyond.
So,
Like my light speed behind me here. Yeah, Steve, before you go there though,
yes.
I was looking at this right before we started the live cast, and I don't know, it was my Algebra 2 teacher, maybe it was my pre-cal teacher. We talked about some of this stuff, and I remember just looking at what's the difference between those two things. And I note that I've got a cube on the top and a cube on the bottom, which kind of gives me the idea that, gosh, any multiple of one of those two cubes is going to end up being my limit as I go to positive infinity. So I probably wouldn't have shown that middle step. Is that okay?
Probably, because once you learn about that middle step, then there's usually a theorem in most textbooks that say, look, if you have a rational expression and the degree in the numerator and the degree in the denominator is the same,
right,
then the limit as x goes to infinity, or the horizontal asymptote, is the quotient.
Sure.
This fraction m/1. So that's fine. And that's probably why you wouldn't see a problem like this on the AP Calculus exam. But yes, you're absolutely right, Curtis. Absolutely right. So, wait a minute. Why don't I have to look at the limit as x goes to -infinity? I'm gonna suggest that you throw that out there for the chat room, Curtis.
Oh yeah, I like that.
Why don't we have to look at the limit as x goes to -infinity? So we know that m is equal to -5. So let's see, I'm going to use that -5 here for m. And I'm going to use that point that was given to me, that point on the graph, 6 - 5. I'm going to plug that in. Let's see, I'm going to plug in x = 6. And I did a little bit of simplification. That's got to be equal to -5. And holy Toledo, I got a couple of large numbers there, but I got a equal to 4. And so if I add those two values together, -5 plus 4, I got a sum of -1. And wow, that's a great question. Okay. Now, sort of related to this, little different, there's some m's in this, I guess, but this was part of the same question, I guess, that Zach posed. And it says, for what values of m will the line y = 12 be a horizontal asymptote on the graph of this expression? Well, wow, this is a pretty cool expression. It's not really a rational expression because, jeepers, it's got an exponential function in there, 6 to the -x in both the numerator and the denominator. So let's see. I'm going to take a look at what happens as x goes to infinity. Now, I'm going to make sort of an argument about this, but this is another question, Curtis, that you can throw out into the chat, is how would I show this limit more formally? Okay, this is not, and I'm glad you asked that question, by the way, about the problem up above. This is not like the one up above. It's not a rational expression.
Right. That's kind of why I asked that question, because I knew we were headed here, and I was like, I did the same thing in my mind, and I know that wasn't really okay.
So how do you do this one formally? Let me see if I can argue this one a little informally. As x goes to infinity, let's see, what's 6 to the minus x? Whoops, I'm sorry. What's 6 to the minus x doing? Well, let's see. 6 to the minus x is actually going to 0, right? Because that's really 1 over 6 to the x. So that's 1 over 6 to the x with x increasing without bound. The whole fraction is going to 0. So that means that these two terms are really going to 0. So as x increases without bound, well, the expression really looks like this. And then, Curtis, here's where your rule sort of kicks in. This really, as x gets bigger and bigger, just looks like m over 4. And so if I want the horizontal asymptote to be 12, I set that expression equal to 12, and son of a gun, I got an m equal to 48. Interesting. Okay. Well, let's take a look and see what happens as x goes to minus infinity. Yikes. Well, I'm going to try to argue this one also if I can. Let's see, as x goes to minus infinity, as x goes to minus infinity, yikes. What's happening here? Well, the way that I'm going to argue is that as x goes to minus infinity, this is really going to 6 raised to something very, very large, 6 raised to something very, very large. Here's a very loose argument. As x increases without bound, we know that these exponential functions increase much more rapidly than a linear function, than a power function. And so as x is decreasing without bound here, these are the two dominating terms. And so that really looks like just m over 1 or m. And if I want the horizontal asymptote to be 12, that would say that m is equal to 12. So I will put this word off to the side here with a question mark. I've made some arguments for those limits. I might ask now, how would you do those a little bit more formally? Now,
I posted that in the chat asking how we might show that more formally, and hopefully we'll get an idea or two rolling in here in a second.
Okay. Now, here's a couple of graphs of these expressions, one where m is equal to 48 and one where m is equal to 12. And there's all kinds of interesting questions going on here. Calculus questions, even pre-calculus questions about this graph. I've drawn in the horizontal asymptote at 12. And if everything's working out, I think you can see two colors here. Now let me take a look at the green graph first. This is where m is equal to 12. That's this one. I'm sorry, I'm drawing with a blue pen on the green graph. Anyway, it kind of looks like here that there may be a value that is not in the domain of this expression when m is equal to 12. It kind of looks like there may even be a vertical asymptote here. So I'm going to
hold on. I'm going to ask everybody if they think there is one.
I'm going to put a couple of questions off to the side. What's the domain here? And once you figure out the domain, well, jeepers, is there a vertical asymptote? Now take a look at the blue graph. This is more relevant. I'm going to draw the blue graph and outline that in blue. I don't see any part of the blue graph to the left-hand side. Well, all right, to the left of y equal the y-axis. So once again, what's the domain when m is equal to 48? Is there a vertical asymptote there? Why isn't there any part of the graph over there on the left-hand side, to the left of the y-axis? Is there a maximum value here if the domain is all real numbers? Wow, all sorts of good questions here. And for all of those good answers, I'm going to turn it over to Tom.
All right.
All right, now we get to look at the technology to see. This is such a fun question.
This is a cool question.
Yeah, it really is.
Who posted this question, Steve? Just
this was Zach Sarver.
Okay. All right. Well, thank you, Zach, for this this question. We're enjoying playing with it.
Okay, so if you guys can see my 84, okay, it's What I've got in for Y3 is actually the parameter with the M parameter in there. It's the general function. So I don't have a specific value for M. Actually, I do. On the 84, all your variables kind of by default have some value in them. I think the default value is 0, but this is something we can store a value for M. And so what I'm going to do is just go to the calculator screen. And let's see, one of those values for M Steve was talking about is you could put in 12 for M.
So
store. Go
okay.
ahead.
Well, go ahead while you're doing that. But we did get a response here from Cheese, Capo. Good name. They looks like X cannot equal 1. So it appears that X cannot equal 1 on the domain for the function with a horizontal asymptote at Y equals 12. So
That looks that way.
it does look that way. I will admit, I certainly felt that way also.
And I think might have forgotten to, I've stored my value.
You forgot to turn on the graph.
I need to turn it on. There we go. There we go.
There we go. So let's see if the 84 kind of confirms this, or if we've got.
All right. So I'm only seeing a little bit of the graph. This is the, I think this would have been the Steve's green graph. And so I'm seeing this, there is an asymptote. Actually, for any value of M, you're going to have one horizontal asymptote at M over 4, Y equals M over 4, and another one at Y equals M. Because Steve got those were his limits as X approached plus infinity and minus infinity for just the general function. So there's M over 4, and that's for M equal to 12. That would give us 3. I'm going to need to get a little different window here. I'm going to manipulate the Y here. I'll tell you what, I'll just multiply it by 10. And graph.
Oh,
that is correct, Tom. I did not draw in the other one on my graph because I guess the question asked only about Y equals 12, but that is correct.
That's right, yeah. And your other graph, your Y scale just didn't go up high enough to reach that other asymptote. So we would actually expect for M equal to 48 to see a lower horizontal asymptote at 12, which would be 48 over 4, but another one up at Y equals 48.
Right, right.
Now this thing still is looking like, wow, kind of looking like a vertical asymptote maybe. Maybe a little bit to the right of -1. I know somebody on the chat said, you know, somewhere around -1, it looked like there might be a vertical asymptote.
Yeah, it looked like it was at -1, but now just based on this picture, it looks like it might be closer to a half or something, -1/2 or so.
I'm gonna shift my, oops, let's see, actually, let me, my Y min -10, and let me put my Y max up to 80. And let's graph this again and see what we get. Oh, looks like actually there might be a maximum here instead of a vertical asymptote. And if we quit out of here, I'm just going to store a new value for M. We put in 48, store that for M. And graph again. This is that second, or the blue graph for Steve. They all came up black for me. But this asymptote down here, well, I can trace so we can, oh, here we go. Y equals 48 happens to be right here. And you can see this horizontal asymptote is lining up with that.
Yep.
We trace to the right. We can see we're approaching Y equals 12 as we approach constant infinity. So both of those graphs, and I'd have to change my window even more. Let me go up to a Y max of 200. Oh, didn't quite make it onto the screen, but there's actually a maximum there.
So, Tom, I don't want to steal your thunder here, but I'm going to ask you a question, maybe a leading question. I don't know. It seems like, I mean, yeah, this graphical sort of picture, or at least looking at the entire graph, gives me an idea that, yeah, there is a maximum there. But could we have investigated this maybe in a different way, maybe a different set of reasoning? Like, what would it take to make a vertical asymptote, right?
Sure, and some great questions, Curtis. So actually was taking a little bit of a look at that before we got online here, and you can see in my Y2, what I've got there, you may recognize that that's the denominator of that function, just by itself.
So 4x plus 1
plus 6 to the minus
yeah.
x, which I've written as 1 over 6 to the
yeah.
x, which
yeah.
Steve mentioned was another way to think of what that quantity represents.
Yep.
And so what I'd be curious about is, if we really did have a vertical asymptote, that would suggest there'd be some place where the denominator was 0.
Right.
And so what if we just graphed the denominator and took a look at that? So I'm just going to graph the denominator. Let me turn on my Y2. And let me get just a regular, I'll do a zoom decimal window here. So here's the graph of our denominator. Okay, so this is just that 4x plus 6 to the minus x. And it never actually equals 0, at least for these values. Now you'd have to make a more detailed formal argument about why that can never equal 0, but it looks like it gets down between 0 and 1 is the lowest that graph gets. And if we trace on it, where we saw, let's see, this is close to where, it's not far away from where we actually saw the maximum on those two. And that's kind of making sense because that's where our denominator is smallest. So the smaller your denominator,
right,
the fraction.
You're gonna, yeah.
So it kind of makes sense that these are work. Now, of course, we also had a numerator that's exhibiting some behavior, but so it looks like, so this function, because the denominator actually is never 0. Another way to investigate this is you could graph 4x and 1 over 6 to the x separately and think about how they combine in value.
How the sum might work there, right?
And that's another place where you can see, oh, that'll just never be 0. There'll never be a place where the 4x will more than cancel out the 1 over 6 to the x.
It's fascinating to me, actually, that it got this close to 0, because when I think about 6 to the minus x and how large that is, not very far from 0, negative, it just didn't occur to me that we would be even that close to 0.
I don't know about you guys. When I first saw those graphs that Steve put up, my first inclination was, oh, I think there's a vertical asymptote.
Yeah, I think everybody would raise their hand on that one.
Yeah,
I certainly did.
All right.
Tom,
this is a really good one. So before we jump into the next question, Steve, Tom, I'm going to get your expert opinions here. We've got a discussion going here asking about the trig identities and how much students should know or have kind of in their toolbox as they go into the AP Calculus exam. And I know Mark Crowley has made some talk about that the AP Calculus exam is not supposed to be a trigonometry exam. So there's that limit, right? Yep. But then just how much should we have in our toolbox, in our toolkit?
Well, my philosophy is the more you have in your toolkit, the better off you are. Have the right tool for the job.
Yeah. Okay.
Is the AP Calculus exam, is there ever going to be a question on there that requires you to know a certain trig identity? I don't know if I can answer that. but if you know certain trig identities, it may make solving certain problems easier. No
It
question.
certainly makes you, yeah, it certainly makes the trig identity thing a little bit easier, right? Makes several of the problems
Easier.
much more recognizable.
Yep, agreed.
Yeah, I think the definitely the Pythagorean, I call them the Pythagorean identities. That's not just sine squared plus cosine squared, but also the ones involving tangent squared and secant squared. I think those are pretty good. We just use those so often. They're good to have in that toolkit, like Steve mentioned. And the ones that are a little bit more involved, like double angle, the thing is, boy, those are really important when we're doing techniques of integration. They save our day to pull those.
Yeah, I saw the double angle one. I mean, I was just kind of thinking about that. Certainly as one that would be worth having in your toolkit.
But there's certainly not some long laundry list of these identities that you're expected to memorize. There's a handful of ones that are just real handy to know, and it's certainly, if you don't have to be looking those up, or you have those at your beck and call in your mind, that's nice to have.
Yep.
Certainly, and it helps recognizing strategies for solving problems too, right? Just you can kind of see sort of the structure, if you will, of a particular expression, especially in those integration problems. I would expect that's certainly helpful. All right.
All right.
Sorry to disrupt there. I just wanted to make sure we answered that and kind of got that going.
Okay, well, this is a nice problem too, from Allison Myers-Abel. This is a great problem. I'm going to try to attack this one graphically. And Tom, I apologize. I should have mentioned this earlier, but I envision you creating a cool TI-Nspire file that's dynamic to show this one, because I'm going to try this one graphically, and then I'm going to try to back it up with a little bit of an argument here. So here's the graph of a function f. I've added a grid in here to make this a little bit easier to see. If there is an open circle there at 6, 3, there's a closed dot or a solid dot at 6, 1, and this says find each limit if it exists. Well, let me arrow down here just for a minute. I'm going to look at these 3 limits. So I'm going to look at 2 one-sided limits and then the overall limit, but let's take a look at this one first. And the way that I want to attack this is, since I don't have an algebraic expression for f, I'm just going to think about, well, what is this expression really asking me to do? We know that that is really just the slope of the secant line. So let's see here. I'm letting h go to 0 from the right-hand side. So this is just as if I'm taking points here close to 6, and I draw in the secant line, and the secant line is right on that curve. So it has the same slope all the time, the same value all the time. And I think that value is just a -1/2. So that's kind of a neat question because it's graphical in nature. I don't have an algebraic expression for f. And let's see what happens if we try to come from the left-hand side. So I'm going to arrow up and down a little bit here, Curtis. I'm taking a look at the limit as h goes to 0 from the left of this expression. Once again, I'm taking a look at the slope of a secant line just to the left of 6. So I'm going to draw in a couple of them, and I apologize for this, Curtis. It's a little nerdy, but I'm going to try to use a ruler here.
Well, that's all right. That's okay. Now, while you're drawing in that, I'm going to have Tom look at something. There's a post here on that number 3 that we were just looking at. Pamela wrote in that her students would rewrite the function as mx or m times 6 to the x plus m divided by 4x times 6 to the x plus 1 to see the limits a little bit easier.
I think that's an excellent suggestion.
I think that's a really cool, I thought that was very clever.
Yeah, fantastic.
All right, so what I've done is I've drawn in a couple of these secant lines. As h goes to 0 from the left-hand side, we're approaching 6 from the left-hand side, and we're taking a look at the slope of those secant lines. And although it may not look like it, Curtis, those are perfectly straight lines. And I wonder if you can tell me, what does it look like, the slope of those lines? What does it look like they're approaching?
So they're getting steeper for sure.
Steeper and steeper.
Mm-hmm.
And in fact, if you take a look at my first one here, the slope over here of this one would be negative. And so they're getting steeper and steeper, larger and larger negative.
Larger and larger. Yeah, negative. Mm-hmm.
Yeah. So in fact, I think this answer here is either D and E, or as we've talked about before, minus infinity.
Mm-hmm.
Now, here's a way to look at this using some of the notation that I introduced just a little bit earlier. Please forgive me for this, Curtis. This is the limit. As h goes to 0 from the left-hand side, this is f of 6 plus h. This is the way I'm going to argue on this one. I know what f of 6 is by looking at the graph. It's 1, and there's an h down there in the denominator. Now, what happens as h goes to 0 from the left-hand side? Well, this expression is getting closer and closer to 6. That means f is getting closer and closer and zeroing in on 3. So that means this numerator is getting closer and closer to 3 minus 1, or 2. And the denominator is getting closer and closer to 0, but how? Negatively. And so there's another way that I might argue a little bit more algebraically, perhaps. Since the numerator is approaching 2, the denominator is approaching 0, small negatives, the whole limit is approaching minus infinity. That's a neat question, and it's very easy now to answer this last limit, since the limit from the left and the limit from the right do not agree. This overall limit does not exist. So that was a nice question too. Cool. Tom, anything?
That is a cool question.
Anything technology there?
Well, let's see. I am entering it as we speak.
Okay.
Let's see if it looks okay. All right.
All right, I'll switch it to you. There you go.
All right, I'll give it a shot. So to, again, you guys can let me know if that's looking
I can
okay.
see
This
your
is a
Inspire
TI-Nspire screen now. And
Sure can.
thing is, I don't think this exactly matches your function looking at the graph, but this was something I came up with to just give us something graphically to look at. You know, the linear piece was not so hard. Yeah, I noticed. I'm not sure that was a parabola, and it's clearly not the right one here because it should go through
the origin.
It looks like. So I would need to tweak that a little bit. But this is, I think, just for teachers with whichever technology you're using, whether it's 84 or you got a CAS or something like the Inspire. Some of these things, certainly this particular problem was intended to be done purely graphically through reasoning. But you may very well want to create these kinds of graphs on your technology so that you can then interact with them. So for example, you could do something like a trace, or what we'll see maybe with time permitting, you might have a couple of functions like this, and you could even compose them or combine them in some way. So that's all I was going to show. And I think last week, you know, we talked a little bit about split defined functions, piecewise defined functions.
Mm-hmm.
You can definitely do them on either the 84 or the Inspire, and it's a really handy tool to have. So I'll turn it back over to you, Steve.
Okay. Okay, these last couple were very clever. This one was from Carla Duke Rossi. And we have the graphs of two functions. On the left-hand side, we've got a graph of y equal f of x. On the right-hand side, we've got y equal g of x. Now, we don't have them described algebraically, but you know what? They're not too bad. We could if we wanted to, I'm pretty sure. And we're asked to find the limit as x goes to 0 of this sort of composition here, g of f of x plus 1. Now, we talked about a couple of these last week, like this last week. And the way that I'm going to attack this is I've got to take a look, first of all, at what this argument is doing as x goes to 0. So let's see, as x goes to 0, what's f of x doing? Well, let's see, I'm going to take a look at this graph of f of x. As x goes to 0 from both the left and the right, this is kind of interesting. The function near 0 is constant. It's -1 all the time. It's constant. And so as x gets close to 0, that argument is just 0. So I might write this as a limit, and I'm going to use a different variable. As t goes to 0 of just g of 0, t being the argument of g here, but that argument is constant. Well, wait a minute, what's g of 0? I've got to go back over to this graph. G of 0 is just 2. So the limit of a constant function, darn it, is just the constant. Now that's really weird, because if you just look at this graph over here of y equal g of x, and I would ask you, well, what's the limit as x goes to 0 of g? You'd tell me it's 0. This is very odd that this limit turns out to be that solid dot here that's not part of this graph of this function g. That is a really neat question, Carl. I don't know where you found that one, but that's a good one. And Tom, let me just finish up with this one, and then I'll turn it over to you. This is a similar one. Here we want the limit as x goes to 4 of 2 times the cosine of f of x. So let's see here, another composition. And again, f is given to us graphically. We don't have an algebraic expression. We've got an open circle right here and a solid dot right there. So let's see, I've got to take a look at what that argument, let's see what that argument is doing. I'm going to leave the what's underneath the limit here alone for a second. I'm going to write a t in here. What is this doing as x goes to 4? Well, let's see. As x goes to 4, let's see, as x goes to 4 from the right and the left, the function is approaching what? 5.
5.
But 5 from the left-hand side. So I'm going to write that like this. The argument is going to 5 from the left. There's the argument. Now, how do I solve that limit? Well, that's pretty easy, because the cosine function is continuous everywhere. So I can just plug in a 5, and all right, if I do that, I get something like this, 2 times, I think it's around about 0.2386. And in the spirit of the AP Calculus exam, with 3 digits to the right of the decimal, I think I got a 0.567 for that.
Steve, that's pretty good memorization, having those cosine of 5
Memorized, you like that?
into your brain there. Well, I'm gonna call. We've got about one or so minutes left. So if you've got one more, I'd love to see it. And then I've got a couple of things I want to do to wrap us up.
All right, Tom, that's my 6 questions. Anything for you?
No, I think it's a good place to wind things up. Thanks, Steve.
Okay, very good. Thanks, Tom.
Well, thank you guys both very much for your expertise and for sharing and finding those questions. I know, it takes a lot of work checking those out. I certainly appreciate that. And I want to encourage all of the teachers and watchers who are out there, please find questions, email them to me. I'll put my email out there in the chat again. Certainly be happy to pass those along to Steve and Tom as we prepare for the next one. Which, by the way, we're breaking schedule a little bit here. We're going to be on again next week. So exactly 7 days from right now, we're going to be doing session number 3 of Monday Night Calculus, Your Questions, Our Answers, which is really more like our responses, which is awesome. I certainly appreciate that. But I just want to encourage every teacher to encourage your students to watch. We would love to have students on here asking asking their questions to make sure that we're clarifying things. I'm certainly happy to see new teachers on here asking questions, and also want to point you to the blog post. We've got a blog post that has the entire schedule for the year here, along with the links that can be shared, the YouTube links that can be shared directly with your students, so you don't have to email them every week. You could actually just send them the link to the blog post. We'll put that in the chat here momentarily, and then you could actually send that out to your students. Well, I thank you very much for joining us this evening, and we will look forward to seeing you next week for Monday Night Calculus. Good night.